All right, so number 4, taking those 4 derivatives. First, take the derivative of g of x, so that would be, this would be a chain rule. So g primed of x would be take the derivative of the outside, leave the inside the same, multiply by the derivative of the inside. So I guess if I want to clean this up a little bit, the 2x would come in front. G primed of 2 would be where my x value is now 2. Well, I already found g primed of x, and that was the 2x, f primed of x squared plus 1. Therefore, I'm just going to substitute in my x value of 2. So I get 2 times 2, f primed of 2 squared plus 1. So I get 4 f primed of 5. Letter C says g primed of x cubed. So again, I'm going to use the above to get that g primed of x cubed would be 2. The x cubed goes in for x. F primed of x cubed goes in for x. We're going to square that value and then plus 1. So I've taken the derivative already, and then now I'm inputting values for my x. And so in this case, really there isn't much I can do to this, but 2x cubed f primed of x to the 6, because we multiply these powers, and then plus 1. So a lot of people got letter D wrong. And D, the tricky thing was, they're asking you to take the derivative after you find g of x cubed. So the difference is I'm not taking the derivative first. G of x was f of x squared plus 1, so g of x cubed, and I'm going to actually erase this real quick and put g of x. So g of x cubed would be f of x cubed, whole thing, squared, and then plus 1. So I actually get that this becomes f of x to the 6 plus 1. So all I did was find g of x cubed. But now they're saying after I've done that, take the derivative of it. And the derivative of it would be equal to, take the derivative of the outside, leave the inside the same, multiply by the derivative of the inside. So you'll notice that the answers for C and D are different. Number 5, determine where f is continuous. So f would be continuous everywhere except for x cannot equal to -1, because that's a removable discontinuity. Letter B, where is it differentiable? It's not differentiable at x equal to -1 because of discontinuity, and we'll even call it a removable discontinuity. It is not differentiable at x equal to 0 because it's corner. It is not differentiable again at x equal to 2 because it is a corner, and again at x equal to 3 because it's a corner. So these are the values for which it's not differentiable. If they wanted intervals for where they are, so for letter A, the interval would be -infinity until 1, -1, union with -1 until infinity. And then letter B, the answer would be -infinity to -1, union with -1 until 0, union with 0 until 2, union with 2 until 3, and then union with 3 until infinity. Kind of a pain to do that, which is why I gave the non-differentiable point. Remember, differentiability happens as long as it's not a discontinuity. That would be the first type. There's 3 types of discontinuity. There's the removable, jump, infinite, and then actually forgot to mention oscillating. The other 2 ways that for it to not to be differentiable would be a corner. Third way would be a cusp. And the fourth way to not be differentiable would be a vertical tangent. Those are horrible notes, but you get my drift. All right, number 6, find the value of a to make the function continuous. So if you want the function continuous, you would have that the value from the left side is the same as the value from the right side, and we want this at x equal to 2. So now I'm going to substitute in my 2 for my x value, and I get 2 squared minus 3 is equal to a times 2. We get 4 minus 3 is equal to 2a. A is equal to 1/2. Now, B is a tricky question because The only way for the function to be differentiable at x equal to 2 is if first it is continuous. Now, if you remember a second ago, we just found that the only way it would be continuous if a was equal to 1/2. So I'm actually going to rewrite the function because this function here is continuous. Now they want to know if there's a value for a that would make the function differentiable. Now the only way this would work is if the a value is 1/2. So we're going to double check. How do we check if it's differentiable? We want the derivative from the left and from the right to be the same. So the left side's derivative would be 2x. The right side's derivative would be 1/2. We're checking at x equal to 2. So underneath, the left-sided derivative would be 2x. The right-sided derivative is 1/2, and we're checking at x equal to 2. So I'm going to substitute in my 2, and I get 4 is equal to 1/2. The left side derivative and the right side derivative are not the same. So there is no value of a that would make the function differentiable, but there is a value that would make it continuous. I will show you the major mistake for this one. Most people will take the derivative, I'll do it in this corner, of the first function, 2x, and then they'll set it equal to the derivative of the right function, which would just be the a, at x equal to 2. So you get 2 times 2 is equal to a, and you'll get a is equal to 4. So now you made the left and right derivatives the same. Problem is, if you put x equal to 4, or sorry, a equal to 4 into the function won't be continuous. So if you actually put the value in, the left side would be 16 minus 3, which would be 13. The right side would be 2 times 4, which would be 8, and therefore not continuous. So you can't be differentiable unless you already are continuous. So again, yes, there's a value a that makes it continuous, but no, there is no value for a that would make the function differentiable, because the only possible value for continuity is a equal to 1/2. Number 7, suppose there's a function continuous on -5 to 5 and has the following properties. So I get a bunch of y values. I get that f double prime, let's do a little sign chart here, is greater than 0 from -5 until 0. And from 1.5 to 5, it is greater than 0. I would assume then from 0 to 1.5, the second derivative would be negative. We are decreasing when x is less than 3, and increasing when x is greater than 3. Sketch a possible graph. So what would my graph look like? So what I'm going to do is break this function up a little bit more. So before I do that, I'm going to take this blue and just kind of continue all my signs so that when I break up the function, I'll still see the sign. So in yellow, here's my break for 0, here's my break for 1.5, and here's my break for 3. Why is that helpful? Because now I can see that from -5 to 0, I am supposed to be concave up, and I'm supposed to decrease. So the only way that could happen would be concave up and decreasing is this part of the U. Here I am concave down and decreasing. So this would be here, and that would be this side. Next one, I am concave up, but decreasing. So that would be coming down again here. And then the last part here is still concave up, but I'm increasing. So concave up, but this side increases. You can kind of see what the graph will look like if you connect those dark and black pieces. So here, from -5 until 0, I would look like this. But then from 0 to 1.5, I do something like this. And then 1.5 until 3, I do something like this. And then I keep going. Now, right here, you got to make sure there's no undefined. So if you can kind of see, I actually have the graph here. This is concave up, this is concave down, this is concave up. The function decreases until we get to my horizontal tangent right there, and then increases after. So how do you actually make the graph work, and how do you get all your points? The first thing you want to do is graph your points. So it said f of 0 is 2, f of 3 is -2, and then f of 5 is 1. You have to make sure you go through those points. So what I usually do is I start from one of the points that I have to use, and then I go to the right. So from here, that would be this point here. So I'm going to do this type of graph. I'm going to go decrease until I hit x equal to 1.5, and then I'm going to be concave up after. So let's see, 1.5 would be about here. I'm going to go like this, and I'm going to turn concave up, and then I'm going to increase until 5. So the only thing I have to be careful about is I don't have an undefined derivative. The only thing I want to make sure I don't have a corner, and I don't have something like a vertical tangent in there. All right. Then going backwards, I'm actually just going to follow the rest of the graph back. That would be this piece here. So, and then how do you check if you're right? You double check everything. I'm going to highlight. So looking at my second derivative sign chart, I should be concave up, I should be concave down, and then I should be concave up. So somewhere around here, I'm putting my point of inflection. I should decrease the whole entire time until about 3, and then I should increase after. So that exactly happened. That should be my point of my horizontal tangent, my only horizontal tangent. You want to make sure that there are no vertical tangents, and you want to make sure that the graph is continuous. I think that's it.